Hello students, we are finally at our second last topic, right? So please hang in there. We are going to complete our curriculum real soon. Okay, so now we are at topic 21 on periodicity, but fret not because most of the contents of this particular chapter will be something which you can resonate with, and you are actually very familiar with them because you have seen them before in JC1. Okay, so before we move on, let us look at some of the learning objectives, because after we have looked at the learning objectives, then you will believe what I've mentioned earlier on, that you are familiar with most of the contents in this particular chapter. Okay, so if you look at 5A, students required to recognize variation in the electronic configuration across periods and down a group. Well, I mean, this will be easy because electronic configuration under the first topic on atomic structure is something which you are very familiar with. Yeah, it's the first topic you studied when you enter the school, right? 5B describes and explain qualitatively the trends and variation in atomic radius, ionic radius, first i.e. electronegativity, also something which you are very familiar with from the topic on atomic structure and physical periodicity. So in that sense, we do not really need to delve too much into them. If you need to revise, please go back and revise the first topic. Okay, 5C interprets the variation in melting points. Okay, so I think this is something which you should be quite happy with, because when you look at melting points, electrical conductivity, and then you need to explain in terms of structure and bonding, so you know that we are really looking at the topic on chemical bonding. Okay, so definitely terms such as metallic, giant molecular, or simple molecular structure should come into play. 5D, describe and explain the trend in volatility of the group 17 elements in terms of instantaneous dipole-induced dipole interaction. Essentially, this is similar to dispersion forces, which you are familiar with from the topic on chemical bonding. Okay, yep. 5E onwards are probably things that are newer to you. Why do I say newer? Because you have not encountered them directly in any learning objective, but you have definitely seen them before in the topic on chemical bonding. Why is that the case? Because you have been asked to draw the dot and cross diagram, say for ionic compounds such as sodium oxides, magnesium oxides, aluminium oxide, etc., and then simple covalent compounds such as sulfur trioxide, PCl5. Okay, so you should be familiar in the drawing of these structures. Okay, but do take note of one very important ideas in your learning objective. You are basically required to state and explain the variation in the highest oxidation number of elements in the oxide. Yeah, so these are the oxides, highest oxidation number, and the chlorides. Okay, so basically, in short, only the oxides and chlorides are in your curriculum, and those of the highest oxidation states. Okay, anything with the next oxidation state will be based on application question. Okay, the only examples I can think of would be for phosphorus will be phosphorus 3 oxides, and then for sulfur will be sulfur dioxide. Okay, and for the chlorides will be phosphorus trichloride. Okay, do note, I mean, I'm sure you notice that for the chlorides, right, there isn't any examples on sulfur, because sulfur has quite a number of examples of chloride. You can have SCl2, you can have SCl4, you can have SCl6. Yeah, so chlorides based on sulfur is not in your curriculum, but it can come out as an application question. Okay, you also notice that oxides based on chlorine is not in your syllabus. Okay, because it does get a bit complicated. Yeah, but it can come out as an application question as well. Okay, so you're supposed to state the variation in terms of the bonding, okay, of the oxides and chlorides, as well as their reaction with water. Okay, you are also required to talk about the acid-base behavior of the oxides and the hydroxides. Okay, and then some of them are amphoteric. So for example, you are aware that Al2O3 and AlOH3 are amphoteric, so you need to talk about them as well. Amphoteric here means substance which are able to react with both acid and bases. Okay, so for the chlorides, you are supposed to describe and explain their reaction with water. Okay, sodium chloride and magnesium chloride will be more of dissolution in water to give you the corresponding cation and chlorides. AlCl3, SiCl4, and PCl5, largely you expect some form of hydrolysis to take place. Okay, yep. Then suggest the types and structures and bonding present in the oxides, chlorides from observation of their chemical and physical properties. So basically, you are supposed to suggest whether they are existing as ionic oxides, chlorides, or covalent or simple covalent oxides and chlorides. Okay, yep. And 5F. 5F is largely 5F and 5G. They are largely learning objective focusing on group 2 and group 17. Yeah, do take note of it. Okay, so for 5F, we are supposed to describe and deduce standard reduction potential values. This is something you learned from the previous topic on electrochem. Okay, the relative reactivity of elements of group 2 as reducing agents. Okay, so metals are largely reducing agents. We all know that, but the focus in this particular curriculum for topic 21 is on reducing agents. Okay, and group 17 as oxidizing agents. I think you might have heard from me saying that fluorine is the strongest oxidizing agent known to mankind because of its really huge standard reduction potential of 2.87 volts. And then this is followed by chlorine with a standard reduction potential 1.36 volts. Okay, and then bromine and iodine. So you're supposed to talk about their trends. And then for thermal stability, you are supposed to talk about group 2 carbonates. Okay, and this is a hot favorite recall kind of question. Supposed to talk about the stability of carbonate in terms of the charge density of the cations. How does it affect and what does it do, and how does it polarize the anion? So you need to discuss the polarizability of the large anion. Yeah, so basically high charge density cation will distort the electron cloud of the anion, and in the process weakens the critical covalent bonds within the anion and cause it to decompose. Okay, you need to be able to come up with explanation related to that. And then group 17 hydrides talk about their stability with regards to their bond energies. Okay, so you can look out for them at the data booklet. You know that HF has the strongest bond energy. I think it's about 560-ish kilojoules per mole, and this is much stronger than HCl, which is about 430 kilojoules per mole, and then followed by HBr and HI. Yeah, so that is what they are talking about. And usually HCl and HBr, they will decompose to give us hydrogen gas and chlorine. Okay, and then objective 5H predicts the characteristic properties of an element in a given group by using knowledge of chemical periodicity. Yeah, so this is largely a application learning objective. Yeah, so after you have gone through periodicity, you need to be able to form some idea. Let's say we give you a new element, say gallium. Yeah, okay, so are you able to predict that it is amphoteric because it shares some sort of a diagonal relationship, or it's probably in the same group as aluminium? Yeah, something along those lines. You need to be able to explain. Okay, then finally 5I deduce the nature, possible position in the periodic table, and identify unknown elements from given information of physical and chemical properties. Yeah, so again, this is largely an application learning objective. Yeah, so if we're going to stretch you a little bit, we might ask you questions, for example, related to elements in the 4th or even the 5th period, or even the 2nd period as well, because if you look at the whole objective here, we are largely focusing on period 3 elements. Okay, that is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, although we are not talking too much about chlorine and argon, because most of you would have learned some of it in secondary school and O levels. Okay, particularly group 1 and group 18. Yeah, so group 1, they are what we call the alkaline metals, and group 18, the noble gases. Yeah, although you don't learn them explicitly in the A-level curriculum, but whatever you have learned in secondary school, I think you need to be able to recall some of them. Yeah, okay, up to this point, please do not go and revise what you have learned in secondary school. I think what is most important is just go and maybe be familiar with their chemistry as much as possible. Even if you don't revise them, whatever you know now should be more than enough. Okay, and you notice that a lot of the ideas we covered in this particular topic will be using ideas, and especially physical chemistry ideas you have learned last year and this year. Okay, do take note of them. Okay, so without further ado, we'll move on to the introduction. I don't think I have much to talk about except by asking you guys to read through some of these things. Periodic table. Okay, and of course, as I mentioned, we are focusing on period 3 elements, so from sodium all the way to argon. Elements wise, you need to know that sodium, magnesium, aluminium, they are metals. Silicon is a metalloid, otherwise known as a semi-metal, so it behaves as a semiconductor in this case. Phosphorus, sulfur, chlorine, argon, they are non-metal. Okay, so with the relevant electronic configuration, do take note if you forget what you have learned under atomic structure. This particular electronic configuration written for you is the short form electronic configuration. If you are asked in a question to write down the electronic configuration for say sodium, right, you have to write the full version. In this case, 1s2, 2s2, 2p6, 3s1. Okay, yeah, and it is important for you to be able to recognize the number of valence electrons in the outermost shell, and these are main group elements. Okay, so sodium and magnesium, they are under the S block, aluminium all the way to argon under the P block. Okay, you need to be familiar with them. Okay, so they are in the same period, so they have the same number of principal quantum shell, right? Okay, now we'll just take a look a little bit at the background information. Sodium, as you have learned in secondary school, very reactive and soft metal, so they must be stored in oil in order to prevent oxidation by air. Yeah, so usually there will be a layer of oxides found on the surface. Yeah, so normally before we use it, we will use a knife to cut open. Usually a pen knife will do, and then we'll just expose the sodium surface, and then we use it for reaction. Usually the addition of sodium, we tend to use it to generate alkoxides or phenoxides. Yeah, as we know from the chapter on alcohols, sodium is able to undergo redox reaction, or what we call acid metal reaction, with the protonic hydrogen in the OH group. Okay, magnesium, very hard. Okay, so often cut in ribbon strips. Okay, and then they are usually used in fireworks. So in the fireworks, those bright white lights which you observe, they are largely due to the presence of magnesium too. Okay, aluminium sheets is something which you are familiar with from everyday life, but usually the one you encounter in everyday life is largely just aluminium foil, but there are many other uses of aluminium. I think those you learn in electrochem as well, where you use aluminium to make the frame of handphones, and then in this case it's hard enough for you to use it as either a composite materials or use it to make the body of aircraft. Okay, and then for silicon, semiconductor, yeah, so it's a metalloid. Silicon chip is used in electronics, something which you are familiar with since you are young. Okay, phosphorus is probably something which you are not very familiar with. You might have seen it before in other aspect of your life, but I mean in chemistry that is, but you probably have not seen many reactions involving phosphorus. Yeah, so there are different types of phosphorus, white phosphorus, red phosphorus, many allotropes. Yeah, so if you are interested, you can read more about them. But in general, for phosphorus, we will use P4 to represent their formula rather than simply just P. Okay, because usually phosphorus exists as 4 atoms bonded together in this particular fashion. Yeah, but this is largely white phosphorus. So for other forms of phosphorus, it has other linkages. Yeah, so at a very basic level, we'll be using P4. Okay, just take note of this. And for sulfur, we'll be using S8. Yeah, having this interesting structures over here, like looks like a crown. Is a cyclic structure with 8 sulfur atoms bonded in a cyclic fashion. Okay, so it burns in a with a blue flame. This is pretty characteristic to form sulfur dioxide. Okay, you might have recalled from chemical equilibrium that it is not easy to form sulfur trioxide. Yeah, so you need to subject sulfur dioxide and oxygen to very high pressure and relatively high temperature with a catalyst in order to produce sulfur trioxide. Yes, so in most cases, you don't get sulfur trioxide, you only get sulfur dioxide. Sulfur has a characteristic smell, difficult to describe to you, but if you have been to hot spring, or in Japan they call it onsen, right? You know, when you soak into the water, you come out, you will smell, there will be a very characteristic sharp smell, that is due to sulfur. Okay, it has been shown that the presence of sulfur helps to cure some of the skin condition, which I'm not sure if it's true. It may be urban myth. Chlorine, yellow-green toxic gas. You will not have seen chlorine in its gaseous state, but you have seen chlorine in various form in either aqueous solution or dissolved in organic solvents. Okay, so it's a very strong oxidizing agent, so you'll react with almost every element to form chlorides. Then for argon, is a colorless inert gas. Thus far, very few compounds were formed with. Actually, for argon, there's no compounds being formed. Yeah, only krypton and above, like xenon. There are many compounds which reacts with xenon, but not argon. Okay, so usually for argon, it's actually used to fill the light bulb. Okay, or some specialized material like a plasma globe. Okay, so it will appear violet when you subject it to a large voltage electric field. Yeah, this is largely due to electronic transition. Okay, so we'll not go too much into them. With that, we'll come to the exercise. Okay, 2.1. Okay, so which of the following statements about the properties associated with ionic and covalent compounds is correct? Okay, so we'll look at the statement one by one. The only covalent compounds with high melting points are those in which hydrogen bonding occurs. This is definitely rubbish. Okay, you can easily think of a counter example, such as giant covalent compound. For example, silicon dioxide. Okay, so there are many examples. You can refute this. Okay, option B, any compound that contains both hydrogen and oxygen atoms in its molecules can form hydrogen bonds. Okay, this is nonsense as well, because it's not always true. If my compound contains hydrogen and oxygen, but they are not bonded to each other, that means that the hydrogen is not bonded to the second most electronegative element known to man, which is oxygen, then the hydrogen will not develop a large enough partial positive charge to form hydrogen bonds. Yeah, so again, this is wrong. Okay, a very simple counter example I can give in this is ether. Okay, so ether is something like this. I can have H and then O and CH and H. Yeah, you see, this compound contains hydrogen and oxygen, but because the hydrogen is not bonded to the oxygen, it's not able to form hydrogen bonds. Okay, so this is incorrect as well. Option C, ionic bonds and covalent bonds cannot both occur in the same compound. Again, this is rubbish. I give you a counter example, sodium sulfates. Okay, so for sodium sulfates, which is very common, is an ionic compound with sodium plus as the cation, okay, and sulfate as what we call the polyatomic anion, or we can call it the polyoxo anion. Okay, so yep, we can easily refute option C. Okay, option D, ionic compounds differ from metals in that ionic compounds do not conduct electricity in the solid state. Yes, so this is correct. Okay, so with that, we'll choose option D as the correct answer. Okay, next question 2. The bond in the compound XY is likely to be ionic rather than covalent if X is a large cation, Y is a small anion. Okay, so first of all, right, we need to be certain about this. If the cation is large, okay, that means that the polarizing power is small. Okay, so we need to do a little bit of revision. So we need to understand two terms here. So cations is associated with the idea of what we call polarizing power. Okay, and anion is associated with the idea known as polarizability. Okay, if you do not know what I'm talking about, please go and revise these two terms under chemical bonding. Okay, yeah. So cation is only associated with the term polarizing power. So that means that if my cation is small and the charge is high, it will have very strong polarizing power. It means that it's able to polarize an anionic electron cloud. Okay, then for anion, if my anion is large, that means that the electron cloud it can be easily distorted. So we say that the anion has high polarizability. Yep. So if my cation is large, the polarizing power is likely to be low. Okay, so in this case, large cation here implies low polarizing power. Okay, small anion here implies low polarizability. Okay, and what about X has a large positive charge? So no, so we prefer X to have a small positive charge. So therefore XY is likely to be ionic rather than covalent if X is a large cation and Y is a small anion, because a small anion is reluctant to be polarized, okay, by a cation, of course. So usually you will see fluorides are anions that are not well polarized, or they can't be polarized that easily. Okay, and therefore ionic compounds containing fluoride usually have very low covalent character. Okay, next we look at question 3. We were told that W, X, Y, and Z are elements in period 3. So I think the easiest way to do this question is just to write out all the elements in period 3, because, well, I mean, that is what the question is about, although you are just given the symbols. Okay, so we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. I'm going to compartmentalize them a little bit into metals, metalloids. Okay, right? So we know that sodium, magnesium, aluminium, they are all metals. So I would expect them to have the highest electrical conductivity and of course pretty high melting point. Silicon is likely to have the highest melting point and fair electrical conductivity. Okay, so for phosphorus, sulfur, chlorine, argon, they are simple covalents, so not likely to be conductors, and their melting point is likely to be on the low side. And then if we look at the information given to us, W has a greater electrical conductivity than Y. Okay, so so for this particular statement, W has a higher electrical conductivity than Y. Okay, so therefore I can say that W is likely to be one of these four. Okay, but lower first IE than X. Okay, so we need to check on this. Y has a higher melting point than W. Okay, so if Y has a higher melting point than W. So therefore, if Y is this, then W must be this. Okay, and then if Y is aluminium, W must be magnesium. Okay, something along those lines. Okay, and Z has a greater atomic radius than W. Okay, if you recall from atomic structure, in the same periods, because electrons are being put into the same valence shell, right? So we learn about this. Effective nuclear charge, okay, is approximately equals to nuclear charge minus the screening effects. Okay, so the screening effect is relatively constant. So as we go across the period, nuclear charge increases. The screening constant stays relatively constant. So you will expect effective nuclear charge to increase across the periods. So I would expect the atomic radius to decrease as I go across the period. And since we were told that Z has a greater atomic radius than W, and we know that W is one of these metals, if we're going to place them in a certain order, right, I definitely will place Z on the extreme left, and then this is followed by W. And because Y has a higher melting point than W, I will put Y next to the right of W. Okay, and then based on everything, we were told that W has a lower first IE than X. So could X be here? So is it possible for X to be here? As we know that first ionization energy generally increase across the periods. Okay, so if we take a look at the first IE trend, right? So we have first IE here. So we have elements. Okay, then we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, sorry, I can't seem to write it properly. Okay, argon, right? Okay, if we write the first IE, draw the trend, you know that it will increase from sodium to magnesium, and then because for aluminium the valence electron goes into the 3p subshell, so it will be on the average further away from the nucleus, so aluminium will drop slightly. Okay, and then after that it will continue to increase until phosphorus, and then for sulfur it will drop slightly because that will be the first instant of pairing. Okay, so if Y were to be silicon, then it does make sense that it does make sense that let's say W is to the left of Y. So let's say W is here. So it does make sense that W will have a lower first IE than X. Okay, so let's say X is here. Yeah, so X can be any of these elements. It doesn't really matter because we were not told any other information about X. Okay, so in this case, the best answer would be donkey. Okay, option D. Alright, we'll move on to question number 4. Okay, which is qualitative. So I will not go into details except just to refer you to your chemical bonding notes, or I will just verbally tell you what I think I will be writing if this is an assessment question. Okay, so we are supposed to state and explain the trend in the electrical conductivity across period 3 elements, okay, from sodium to aluminium. Okay, so first of all, we need to highlight that they are all metals, okay, and being metals, right, it contains giant metallic lattice. Okay, so that is important because you have to highlight the metallic structure. You also need to highlight that the reason why they are good electrical conductor is because of the sea of delocalized electrons being contributed by the valence electrons. Okay, so from sodium to magnesium to aluminium, right, there is an increase in one electrons to the sea of delocalized electrons. So for sodium, there is 1 valence electrons, magnesium 2, aluminium 3. So the number of valence electrons being contributed to the sea of delocalized electron increases from sodium to magnesium to aluminium. So therefore, I would expect the electrical conductivity to increase in that particular order. Yeah, but it is not a linear increase. And the reason why it is not a linear increase is not within the scope, it's outside the scope of the H2 curriculum. So if you're interested, you can read more about it. Okay, it has got to do with the lattice structure as well. Okay, then next question 5. States and explain the trend in melting points across period 3 elements from phosphorus to argon. We need to first write down the structure of phosphorus to sulfur to chlorine to argon. So phosphorus exists as P4, sulfur as S8, chlorine as Cl2, and then argon as argons. Okay, so first of all, we need to identify the key intermolecular forces of attractions when we are discussing melting points. Okay, so these are simple covalent molecules, or for argon it will be monoatomic. Yeah, so we are really talking about dispersion forces. Okay, so the focus in our discussion is in the strength, okay, of the dispersion forces. Okay, or if you prefer, right, you can discuss it in terms of instantaneous dipole induced dipole interaction. Okay, instantaneous dipole induced dipole interaction. What most of your peers in other colleges are learning, it's called ID in short. Okay, so the strength of the dispersion forces is related to the size of the electron clouds. Okay, so it's related to the size and polarizability of the electron clouds. Okay, so the larger the size is, the more polarizable it is, the stronger will be the dispersion force between the molecules. Yeah, so if you simply look at the molecular the molecular formula, so I would expect S8 to have the largest molecular size, and this is followed by P4 and then Cl2 and then argons. Okay, so therefore when we write them out in this order of decreasing molecular size, we are also emphasizing that as we go according to this order, right, the strength of the dispersion forces will increase, and therefore a smaller amount of energy is required to overcome the weaker dispersion forces. So that explains why the melting point will decrease in this particular order. Okay, right. Of course, the question says state and explain a trend in melting point across period 3 elements from phosphorus to argon. Yeah, so when we are answering the question, our focus is therefore not to write them out in order of decreasing or increasing melting point. Okay, so of course we have to go according to this particular order if I'm going to if I'm to interpret the question correctly. Yeah, so therefore I would say, you know, P4 will have a lower melting point than S8, so in this case S8 will be the highest, and then so the trend will go from like P4 to S8, and then it will drop all the way to Cl2, and then after that to argon. Okay, something along those lines. Okay, yep. Then we'll move on to the third section, variation in oxidation number of period 3 oxides and chlorides. Okay, so remember that in our learning objective, right, we are supposed to state and explain the variation in the highest oxidation state of the elements in the oxides. Okay, so as we go across the period, I think it is quite obvious. Sodium oxide will be +1, magnesium oxide +2, Al2O3 +3, SiO2 +4. For phosphorus, it is possible for it to have a +3 oxide as well, but we are not discussing that, so that's +5. SO3, the simpler oxide is SO2, which we are more familiar with, that will be +4. So SO3 will be +6. And then for chlorides, we are simply looking at sodium chloride, magnesium chloride, aluminium chloride, silicon tetrachloride, and phosphorus pentachloride. We are not looking at PCl3. Okay, yeah. So in terms of oxidation number in the oxides, yeah. So I think we mentioned that phosphorus can be +3, +5. Sulfur usually +4 and +6. Okay, and for the oxide chlorine, there exists a few, but we will not discuss them for this particular section, okay, because it's not exactly in the curriculum. If you are interested, you may read more about them. Oxidation number in chlorides. Okay, so it's possible for sulfur to exist +1, +2, +4, and sometimes even +6, but that might be quite rare. Okay, for phosphorus, +3 and +5. Okay, yeah, so I think they are summarized in this particular table, but again, the focus will be on the oxides and chlorides with the highest oxidation states. Yeah, so there are some of these trends that are observed, but I will not ask you to memorize them because sometimes it's by logic. Remember that if you go back to the fundamental level of assigning oxidation states, we will assume that the more electronegative element will take all the electrons. So we'll assume a perfect ionic model. Okay, so with that, you will be able to understand the first bullet point. Oxidation number of the elements in the oxide are always positive, okay, except for F2O. Yeah, because for F2O, right, fluorine is more electronegative than oxygen. Yeah, so for F2O, the oxidation state for oxygen will be +2. Okay, yeah, so do remember, I mean not remember, but you should be able to deduce that based on what you understand about electronegativity values. Okay, so again, I will not discuss too much about these things, except probably you need to be aware that for period 3 elements, because we are filling electrons in the third principal quantum shell, so there is a very high chance that octet expansion is possible. So I think it's bolded here. Octet expansion means that the extra electrons can potentially utilize the vacant 3d orbitals because they are quite close in energy with the p and the s. Okay, so do remember that as well. Then for section 3, we have exercise 3.1. You are being asked which property of the first 6 elements in period 3, sulfur to sodium to sulfur. I can write them down again. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur continuously increase numerically. Okay, so first of all, I think we agreed earlier on that atomic radius decreases as we go across the period because of the increase in nuclear charge and the relatively invariance increase in shielding effects. Okay, so A is definitely incorrect. What about melting points? Okay, for melting points, the increase is, I mean, the trend is not a general increase because as what we have discussed earlier on, silicon will have the highest melting point. Yeah, so it will increase from sodium to magnesium to aluminum to silicon, and then after that, when we go to phosphorus, which exists as P4 molecule, and sulfur as S8 molecule, it will decrease drastically. Yeah, so for melting point, it is not it does not increase continuously. Okay, so this is incorrect as well. Okay, then next for option C, first ionization energy, is it a continuous increase? No, because earlier on, remember, we talked about 2 abnormalities over here. Okay, so from magnesium to aluminium, valence electrons in aluminium found in 3p on the average spend its time further away from the nucleus. So therefore, effective nuclear charge is slightly lowered. Yeah, easier to remove the electron. Okay, and then from P to S, the first instant of pairing occurs in sulfur. So inter-electron repulsion again cause the effective nuclear charge to decrease slightly. Okay, so with that, we are definitely confident that first IE does not increase continuously. Okay, then of course the answer will be D, the maximum. Okay, the keywords, please look at the keyword. Okay, this is the maximum oxidation number. Okay, so again, without even going back, we know that maximum for sodium is +1, for magnesium is +2, aluminium +3, silicon is +4. Okay, phosphorus maximum is +5. You can reach +5, am I right? Because +3 is possible, but +5 is the maximum. And then sulfur will be +6 because of octet expansion, the possibility of an octet expansion. Yeah, so therefore option D is the only option you will pick for properties that increase continuously. Okay, right. So with that, we are done with section 3. We'll move into section 4 next on the properties of the oxides. We will first look at the structure and bonding of the oxides. Okay, so we'll be looking at the first 6 oxides in period 3 as mentioned by the learning objective. So as we move across the periods from sodium to magnesium to aluminium, silicon, phosphorus, sulfur, electronegativity values actually increases. So that means that the electronegativity difference between the element and oxygen will narrow. So that will increase in the covalent character between the bonding. Yeah, so that explains why for the first 3 members, namely sodium oxide, magnesium oxide, and aluminum oxide, they exist as giant ionic lattice with increasing covalent character from sodium to aluminium. For silicon dioxide, it happens to be right smack in the middle, so it exists as a giant covalent compounds. And for phosphorus penoxide and sulfur trioxide, they exist as simple discrete molecules with weak dispersion forces between the molecules. Of course, over here when we say weak is relative, so the dispersion forces is weak as compared to say that between let's say sulfur dioxide or even H2S. Yeah, but because of the relatively large molecular size of P4O10 and even SO3, you would expect the dispersion forces to be relatively strong, so you expect them to have relatively high melting and boiling points. Okay, yeah, so I think the point I mentioned over here regarding electronegativity difference narrowing between the element and oxygen is mentioned in this particular bullet point, so I don't think I want to repeat that. And then moving on to section 4.2 in the trend in melting points of the oxides, I think we have sort of gave the ideas away. Yeah, so you notice that at the physical state at 25 degrees Celsius, sodium oxide, magnesium oxide, Al2O3, they're all solids. I think it is expected because of the strong ionic bonding between the ions. For silicon dioxide being a giant covalent lattice, so you would expect very strong covalent bonds to exist between silicon and oxygen, so that will lead to a very high melting point as well. So you expect it to be about 1700. We can't exactly compare between the bond of covalent, the covalent bond strength as well as the strength of the ionic bonds directly without making any other references, so let us not try to do that. Okay, and for P4O10 and SO3, they are clear-cut covalent compounds, so you expect weak instantaneous dipole-induced dipole interaction between them, or dispersion forces between them. And as I mentioned, the molecular size of P4O10 is relatively large, so I would expect quite a strong dispersion forces between P4O10 molecules. That explains why it sublines at about 360 degrees Celsius, and it exists as a solid at 25 degrees Celsius. For SO3, molecular size not as large as P4O10, so yep, exists as a liquid with melting point 17 degrees Celsius, and that makes sense. Okay, so if you need to revise, please go back to the chapter on chemical bonding. That should be topic 2, and do your necessary revision. Yeah, this is one of the more important relationship. Lattice energy is a good proxy to ionic bond strength, yeah, which is inversely proportional to the product of the charges and inversely proportional to the sum of the ionic radii. Okay, yeah, so do remember this relationship. It's a proportional relationship, it's not an equal sign, so do take note of that as well when you discuss. Okay, moving on, I will not spend too much time discussing the melting points of the rest of the ionic compounds such as MgO, Al2O3, and even silicon dioxide. For silicon dioxide, we are breaking covalent bonds when we are melting it. Yeah, but I thought I just want to mention that in this particular structure, giant covalent structure, it might not be very clear from your lecture notes, but do take note that what you have here is a silicon being surrounded by 4 oxygen over here. Okay, yeah, so you have a silicon over here surrounded by 4 oxygen. Yeah, it might not be very clear from your lecture notes, so do make the necessary adjustment, or you can have a reference to the to the PDF copy online. Okay. For phosphorus and sulfur, as mentioned, they exist as simple discrete molecules. Yeah. So the structure of P4O10 is quite unique. Yeah. So you have the phosphorus right in the middle with a double bond O, and then it is single bond to 3 other oxygen. Yeah. And then each of the phosphorus, right, will be doubly bonded to 1 oxygen. And then right in the middle, you notice something like a chair-like conformation. I think if you are taking H3, you'll be familiar with what I'm talking about. Yeah, so this is known as a chair-like conformation. Yeah, there isn't really a need for you to memorize the structure of P4O10, but of course, when exam requires, then the question may require you to derive it from first principle. Yeah, for SO3, I think it's quite straightforward. For the dot and cross diagram, you know that it is able to form 3 double bond with the oxygen, so you will take on a trigonal planar geometry, something like that. Yeah, so you expect the dispersion forces between SO3 molecules to be weaker than that between P4O10 molecules. Okay. Yeah, with that, we can look at the first exercise, which is 4.1. We were given fiberglass is a mixture of ionic oxides and giant covalent oxides. So you have both ionic and giant covalent. Which of the following is unlikely to be a constituent of fiberglass? Yeah, so question is unlikely constituent. So we are looking out for ionic and giant covalent. Yeah, so MgO is ionic, so likely to be a constituent. Al2O3 is ionic, likely to be a constituent. SiO2 is giant covalent, likely to be a constituent. Okay, P4O10 is simple molecular, so not likely to be the constituent. So the answer to exercise 4.1 is D. Okay, with that, we'll move on to the acid-base behavior of the oxides and hydroxide. Okay, so earlier on we talked about structures and bonding. Okay, so now we are back to acid-base behavior. Yeah, before I move on, I just want you to take note that at the back of your mind, right, you should be aware that their acid-base behavior is related to their structure and bonding. Okay, so just take note of that. Yeah, so I'll just jump straight. Okay, so for ionic oxides, they will tend to have O2 minus as part of the ionic lattice, and O2 minus tends to hydrolyze readily in water to give OH minus, and OH minus is a stronger base that is possible in water. So in that case, the hydrolysis will lead to the production of hydroxide, which will increase the pH to close to 14. Yeah, so ionic oxides tends to be alkaline. Okay, for covalent oxides, again, they are usually classified as acidic because the hydrolysis of the relevant bonds tends to lead to the production of H+, which later on I will showcase to you some examples. Yeah, the one that is smack right in the middle, for example, aluminium oxide, is what we call amphoteric, and I can explain a little bit here. Yeah, you'll notice that the covalent character actually increases across the period for sodium all the way to sulfur. Yeah, so in that sense, right, silicon, or rather I should just circle this, silicon dioxide, phosphorus 3 and phosphorus 5 oxide, and sulfur dioxide and sulfur trioxide, they are all acidic oxides. Okay, and do take note that they are all covalent in nature. For sodium oxide and magnesium oxide being ionic, they tend to be basic. Yeah, so what is the reason? As mentioned earlier on, because the O2 minus tends to hydrolyze in water to give OH minus. Okay, what about Al2O3? Okay, Al2O3 is interesting because it is an ionic compound with significant covalent character. So that means that it behaves both as an acid and a base, and with the ionic and covalent character, it's able to take on both characteristics. Yeah, but truth to be told, its amphoteric behavior is largely due to the fact that aluminium 3 plus has high charge density. Yeah, so if you go through the notes, they might just go into details later on, but I will just urge you to think about the structure and bonding as related to their or rather their acid-base behavior is intimately related to their structure and bonding. Yeah, so usually compounds that are clear-cut ionic or very close to ionic characteristic, they tend to be basic. Covalent characteristic or covalent oxides tends to be acidic, and for Al2O3 it is an ionic oxide with significant covalent character, so it's like it has the best of both worlds, so it will be amphoteric. That means that it can react with both base and acids. Okay, yeah, so with that we'll just move on with the discussion. I know it's a little bit boring. Periodicity as a topic is quite boring. You just have to bear with me discussing some of the details and where possible try to relate to some of the chemistry which you have learned. Okay, so for basic oxides such as sodium and magnesium oxide, they react with both water and acids, of course. Yeah, so for sodium oxides, it will dissolve completely. Take note that the reaction is vigorous, exothermic due to the production of a lot of heats, and that explains why it even the exothermicity can even be felt in cold water. Okay, it forms strongly alkaline solution. I think that can be easily understood because of the complete hydrolysis of O2 minus to give OH minus. Yeah, there isn't a need to memorize the two equations because you can easily derive them when you work it out. Okay, do take note that reaction with acid tends to be more exothermic than that as compared to reaction with water. Okay, it tends to have that relationship. You can ask yourself why, or you can think about it if you wish to. For MgO, right, the reaction with water is very slow, largely due to the fact that it has limited solubility in water. Yeah, and because of that, the final pH of the solution tends to be lower than that of sodium oxide, so it hovers around 9-ish. Okay, reaction with acid tends to be complete. In normal circumstances, that is, it will form a salt solution. Yeah, so these are the two balanced equations. For MgO, the production of magnesium hydroxide results in a solid compound, and magnesium hydroxide partially ionized in water to give Mg2 plus and OH minus. Yeah, because of a low concentration of OH minus, that explains why the pH is quite low. Okay, yeah. So for the basic hydroxides, right, that will be sodium and magnesium hydroxides. Okay, so I'm sure you are very familiar with their chemistry. Okay, you have encountered them in secondary school and even in stoichiometry and redox. Okay, so they will react with acid to form salt solutions and react via the classic acid-base neutralization reaction. Most of you will probably have not seen sodium hydroxide in its solid states. Okay, it actually exists as a white pellet. And how do we prepare the sodium hydroxide solution? We'll just dissolve the solid to give a colorless solution, but the reaction is highly exothermic. Okay, and the reaction with sodium hydroxide and acid is also highly exothermic. And if you recall from the chapter on energetics, yeah, essentially that is the reaction between OH minus and H plus. Yeah, so you get an enthalpy change of neutralization to be around negative 55.6 moles per dm cube. Yeah, so if you kind of forget what I said earlier on, you might want to revise on energetics. Okay, for magnesium hydroxide is a white solid. I think you have used it in one of the earlier experiments. Okay, only sparingly soluble in water. Okay, so it will give you a colorless solution as well. But if you use HCl to react with it, the reaction is complete. Okay, because essentially you have the H plus surrounding the OH minus at the surface of the ionic lattice, and then slowly but surely the H plus will consume all the OH minus via acid-base neutralization reaction. Okay, the special one which I guess you are also familiar with since secondary school is aluminium oxide, which is N4-steric. Okay, the usual explanation given is that the bond is a covalent bond with significant covalent character. Of course, here it's written as some covalent character. Yeah, so the mixture of ionic and covalent character allows it to display both basic and acidic property. Okay, if you just put Al2O3 in water, you are not going to expect it to dissolve, so it will just remain as a solid. If you put it in acids, after a while it will react via acid-base neutralization reaction, and then you will get Al3 plus as the cation. Okay, in the presence of excess bases, so for example in when we have a lot of OH minus, then the Al3 plus will tend to complex with OH minus, and then it will result in the aluminate complex ion. Yeah, that explains why when you perform qualitative analysis, when you add sodium hydroxide dropwise to Al3 plus, you get white PPT which dissolve in excess to give you a colorless solution. Yeah, the reason is due to the formation of this particular complex. Yeah. The balance equation, I don't think you need me to demonstrate to you how it can be written. Okay, so it's just a simple acid-base neutralization reaction as per what we are normally familiar with, except that you need to be reminded that the production of water is of utmost importance. Okay, some students will always ask me whether there's a need to memorize the reaction between OH minus and Al2O3. Okay, so my suggestion is do not memorize. I will teach you how to derive the equations. All you need to do, right, is first write down Al2O3 as a solid. Okay, and then you don't know how much OH minus to add. Yeah, but you know that at the end of the day, right, you are going to produce the products known as aluminates. Okay, so aluminates looks like this: AlOH 4 brackets minus as an aqueous species. Okay, and because I have two aluminium here, so I need to balance the equation. So I will need to have two of these aluminates. Okay, if you do a quick count, you will find that at the end of the day, the equation can be easily balanced. Okay, how do we do a quick count? I think the first thing you might notice is that on the left hand side, there's a total of 3 oxygen. Of course, there's an OH here, so I think the first thing we need to do is to balance the H on the right with the OH minus. Yeah, so if you take a look at the number of OH minus on the right hand side, there's a total of 8 OH minus. Yeah, so if you simply just add the 8 OH minus in, you realize that later on you run into problem of charge balance. So my suggestion is we don't do that first. We'll first balance the charged. Okay, so on the left -1 charge, on the right -2. So naturally I'll just put a 2 OH minus here to balance the charged. Okay, so with that, if you do a quick count, there's a total of 5 oxygen on the left and 2 H as well, and then on the right hand side, 8 oxygen and 8 H's. Okay, so if you do a quick cancellation, yeah, 5 oxygen I cancel. Over here I'll left with 3 oxygen, and then 2 H's I cancel, I'll left with 6H. Yeah, so the final balance equation is I'm going to just balance with a H2O on the right hand side. H2O. Oh, sorry, my apologies. What am I talking about? The H2O should be written on the left hand side. Okay, so because I'm lack of H2O on the left. Okay, so I'm going to erase this. Yeah, so I'm going to write plus 3 H2O liquids on the left hand side. Okay, so this is how you balance the equation for the equations between aluminium oxide and aluminates. Okay, yeah, so remember, the most important thing is you need to remember the molecular formula of the complex. If you don't remember, then it will be almost impossible for you to balance the equation. Okay, yep. Then similar to aluminum oxide, aluminum hydroxide is also amphoteric. Yeah, so the reaction will be quite similar. So for aluminum hydroxide is a white solid, insoluble in water. So if you subject aluminum hydroxide to HCl, it will dissolve completely to give you Al3+, Cl-, and of course H2O. This should be a familiar reaction to you in qualitative analysis when you try to shift the position of equilibrium of aluminate in the solution, okay, by adding some amount of HCl, and along the way, because the OH minus is being disrupted, aluminate cannot be present in totality, so some aluminum hydroxide gets precipitated out. So that's why you see a brief appearance of aluminum hydroxide. But if you add the acid too fast, you will not see the brief appearance. You will simply just see the solution remaining as colorless, because any amount of aluminum hydroxide that appears briefly will simply react very quickly with the H+ to give you Al3+ eventually. Okay, yeah, so do remember that. I mean, if you don't remember, you can always refer to your notes, but there really isn't a point to try to memorize all these things. It's better to understand the underlying reason why certain reaction takes place. Okay, then moving beyond aluminium, right, we have the acidic oxides. Okay, so a classic example would be the giant covalent silicon dioxide. So it has no basic properties. Okay, so itself, it does not dissolve in water, or it doesn't interact. Okay, with strong bases under normal condition, there's no reaction. Do take note of it. Okay, although it's an acidic oxide, right? Yeah, but due to the giant covalent structure, it's very difficult for it to react. Okay, so you have to heat it very rigorously, and you need to use concentrated base before any significant reaction takes place. Yeah, so eventually, if reaction does take place, you will form the silicate ion, which is colorless. Okay, yeah, so in most situations in the lab, even if you pour in a base silicon dioxide, otherwise known as sand, it doesn't react. Okay, it will only react in the presence of hot and concentrated bases. Then for phosphorus and sulfur, I think these two are oxides which you should be quite familiar with. Yeah, and of course, I think in our notes we wrote here, even for chlorine, although not in the syllabus. Yeah, so they are very acidic oxides. Yeah, so for P4O10, it will ionize, or I mean, it will hydrolyze, in fact, in water, right, to give you phosphoric acid. You'll notice that it is quite easy to predict whether you get phosphoric acid or phosphorus acid. You can do that simply by looking at the oxidation state of the phosphorus. Yeah, because hydrolysis reaction is not a redox reaction. Remember this. Okay, I repeat, hydrolysis reaction is not a redox reaction. Yeah, so phosphorus 5 oxide will end up with phosphoric 5 acid. Yeah, just remember that. Okay, so it's not a redox reaction. How can we predict the formation of phosphorus 5 acid? Okay, I will not go into details, but basically it is just the breaking down of the structure which you saw earlier on. I think the one with the chair right in the middle. Yeah, but because we do not need to go into the nitty-gritties of the mechanism, then I don't think I will discuss too much. But I think what I can do is simply just to show you what are the bonds being hydrolyzed. Okay, so basically what you are sort of expecting is that when you subject P4O10 to water, the phosphorus center being highly electron deficient, right, it will undergo nucleophilic attack by H2O. So it will undergo some form of addition elimination reaction a few times. Yeah, so eventually the phosphorus center, right, the PO double bond, the pi bond will break and then reform, break and then reform, and then eventually you can just envision that this bond breaks 3 times and then each of them is replaced by H2O, and then after that the H will be lost as a H plus, and then you end up with phosphoric acid. Okay, do remember that this is just a very simplistic view of how the reaction takes place, but I think it helps you enough to understand why you end up with phosphoric 5 acid without any redox reaction. Okay, yeah. So in excess bases, similar to phosphoric acid, phosphorus 5 oxide will result in the formation of phosphates as well. Yeah, and because the hydrolyzed form of phosphorus 5 oxide is phosphoric acid, you will end up with the phosphate with a +5 oxidation state as well. Yeah, so you can just envision it to be a complete hydrolysis to give you phosphoric acid, and then a complete acid-base neutralization reaction to give you phosphate and additional water molecules. Yeah, I know it's a little bit complicated, but it can be viewed in this manner so that it's easier for you to write the balance equation. Okay, I repeat, you can view the reaction with OH minus as first a complete hydrolysis, and then this is followed by a complete acid-base neutralization reaction to give phosphate and water. Okay, yeah. For sulfur trioxide, it's very weird that the current syllabus talks about sulfur trioxide, because in most cases we don't get to see or observe the presence of sulfur trioxide because of its highly reactivity. It has a very highly electron deficient sulfur center, which make it highly susceptible to hydrolysis in that sense. Okay, yeah. So if it were to exist, yes, it will hydrolyze completely to give you a solution which is fairly acidic, pH 1. Okay, and obviously you get a solution known as sulfuric acid, which I think we are all familiar with. Okay, so sulfuric acid is a very strong acid. We all know that. Yeah. But in industry, we don't get sulfuric acid from sulfur trioxide. It normally will form something called oleum, which is H2S2O7, and then before we hydrolyze that structure, which the reaction tends to be a little bit more controlled. And then reaction with OH minus will result in the formation of sulfate and H2O. Again, no need to memorize. It can be viewed as hydrolyzed first before an acid-base neutralization reaction. Okay, yep. 4.4, we have the summary of the properties of oxides across the period. I don't think I will go into details. Please go through them on your own. Yeah, but do remember that our good friend, which smacks right in the middle, is Al2O3. So it's amphoteric behavior. No need to memorize the balance equation. You can simply just derive them as you work through your tutorial problems. Okay, so the best way to work through, to sort of remember and derive the equation is that when you work through your tutorial problems, have the courage to not refer to your notes, because if you just refer to your notes and copy the equation over, then you will not learn a lot, right? Okay. Okay, there's this interesting thing about the pH. Okay, normally we just quote an arbitrary pH. You'll see a lot of school prelim papers as well as a lot of the A-level papers. They seems to quote a pH as though they are gospel truth, like, oh, I dissolve this is the pH 1 I get for SO3. Yeah, but do remember that comparison of pH is only reasonable and fair, right? or of any significance, right, if we know that initially the concentration of the oxides is similar. If they are different, then there's no point in comparing. Yeah, because as you know, a strong acid can also take on a pH of 6 or even 5 when it's very, very diluted. Okay, yeah. So with that, we'll quickly move on to exercise 4.2. Okay, so for the first question, we have X, Y, Z are elements in the same short period of the periodic table. Yeah, so we were told that the oxide of X is amphoteric, and the oxide of Y is basic, the oxide of Z is acidic. What is the order of increasing proton number of these elements? So I think we are very familiar with this already. So if it's basic, it's clear that it has the lower atomic number. So that will be on the left hand side, that will be Y. Then if it's amphoteric, it could be right in the middle. And then if it's acidic, then it will be on the right hand side. Okay, so the only option which fits this is option C. Okay, question 2. Based on your knowledge of periodicity and period 3 elements, predict the nature of Cl2O7. So again, chlorine 5 oxide or chlorine 7 oxide, in fact, is not in our syllabus. In fact, and none of the chlorine oxide is our syllabus. But chlorine being non-metal, I would expect it to be acidic. Okay, so acidic will be the choice here. Okay, then question 3. Which of the following oxides produces the strongest acids when treated with water? So keyword is strongest acid. So obviously I'm going to choose SO3 because we have just discussed it. Yeah, so it's actually a fact which you should know. Al2O3 is not going to dissolve in water. P4O10 will give me phosphoric 5 acid, but it's not as strong an acid as sulfuric acid. Okay, SiO2 will not dissolve in water, so it's out. Okay, question 4. A mixture of the oxides of 2 elements of the third period is dissolved in water. The solution remains approximately neutral. So that means that when the 2 oxides dissolve, that could be some form of acid-base neutralization reaction. Sometimes questions can be this interesting. Okay, so what could be the constituent of the mixture? Okay, so very straightforward. The first thing I will do is I will just strike off any oxide that cannot dissolve. Okay, so Al2O3 can't dissolve. MgO dissolve partially. Okay, but these two, right, will give me a basic solution, so it will not be neutral. Okay, so A and B give me a basic solution. Okay, not neutral. Sulfur trioxide and phosphorus 5 oxide, they are both non-metallic oxides, so acidic, so definitely will not give me a neutral solution. This will result in an acidic solution. Yeah, so the only option left is C, which makes sense because phosphorus 5 oxides hydrolyze to give phosphoric acid, Na2O hydrolyze to give sodium hydroxide. So eventually, if the amount is similar, I would expect a approximately neutral solution. Yeah, so option C will be the choice I'm going to make. Okay, yeah. Question 5. Consider the sequence of oxides. Okay, sodium oxide, silicon dioxide, phosphorus 5 oxide. Which of the following factors decreases from sodium oxide to SiO2 and also from SiO2 to P4O10? For melting points, as we saw from the data earlier on, right, from sodium oxide to silicon dioxide, it increases and then it decreases to P4O10. Okay, so definitely A is out. For covalent character, as we mentioned earlier on, as we move across the periods from sodium to silicon to phosphorus, the electronegativity value increases, so that will narrow the electronegativity difference between the elements and oxygen. Yeah, so in this case, I expect the covalent character to increase and not decrease. Okay, for the pH when mixed with water, right? So sodium oxide, when you dissolve it in water, it gives you an alkaline solution. For silicon dioxide, because it's not soluble in water, so it's neutral. For phosphorus 5 oxide, it will dissolve to hydrolyze completely to give you phosphoric acid. So you're going to get an acidic solution, so the pH decreases. So for option C, it goes down. Yeah, so option C is probably the option which we'll be picking. Okay, but we'll look at option D as well. Solubility in aqueous alkaline. Okay, so for sodium oxide, is it soluble in aqueous alkaline? Yes, because aqueous alkaline contains water, which can allow sodium oxide to dissolve. Not dissolve in that sense, but O2 minus can hydrolyze as well, because O2 minus and H2O will react to give you OH minus in aqueous medium. Yeah, so for the solubility in water, I mean solubility in aqueous alkaline, I expect sodium oxide to be completely soluble. For SiO2, because the aqueous alkaline is just a simple aqueous alkaline solution without strong heating and it's not concentrated, so I do not expect silicon oxide to dissolve. Okay, for phosphorus 5 oxide, of course it will so-called react completely, and in this case dissolve completely to give us sulfate. Yeah, so the shape of the graph will probably look like this. Okay, yes, so I will still stick to my option C for question 5. Okay, yeah. So with that, we'll move on to the next section, section 5 on the properties of chlorides. You'll notice that for the properties of chlorides, there are quite a number of learning objectives. So that includes asking the students to describe and explain the reaction of the chlorides with water, to discuss the structure and bonding presence in the chloride as observed from their chemical and physical properties, and then of course the last two LOs, predict characteristic properties of element in a given group using knowledge of their chemical reactivity, chemical periodicity, as well as deduce the nature and possible position of the periodic table and identify unknown elements. Yeah, so these are the two more difficult learning objectives which I mentioned to you earlier on. Okay, so we'll go through the same kind of process. So we'll first look at structure and bonding of the chlorides. Yep, so sodium chloride, magnesium chloride, as what we learned in secondary school, they exist as giant ionic lattice. Okay, AlCl3, it exists as simple discrete molecules in the vapor phase. Okay, yep, so it will be a little bit different in the solid phase, but yeah, in the vapor phase it exists as simple discrete molecules. Okay, for silicon tetrachloride, it exists as simple discrete covalent molecules as well, and PCl5 as well. Okay, so for the H2 curriculum, we accept that from aluminium chloride onwards, the compounds exist as simple discrete molecules with weak dispersion forces between the molecules. Okay, sodium chloride and magnesium chloride, the idea does not change. Okay, so they still exist as giant ionic lattice with strong ionic bonding between oppositely charged ions. Okay, yeah, so the idea is still about the electronegativity difference between the element and chlorine, which narrows as we go across the periods. Okay, what about melting points? The melting points of sodium and magnesium chloride is not as high as that in their oxides and hydroxides. Yeah, but it's high enough. It's about 800 and 700 degrees Celsius respectively. AlCl3 sublimes from the solid phase to the gaseous phase, and silicon tetrachloride and PCl5 have relatively low boiling points. Okay, so melting point of SiCl4 is -70, whereas PCl5 sublimes at 160 degrees Celsius. Okay, in terms of the appearance, sodium chloride and magnesium chloride appears as white crystalline solids. Okay, so a lot of energy is required to overcome the strong ionic bonding. Aluminium chloride, pale yellow at room temperature. Pale yellow powder. In the vapor phase, it exists as Al2Cl6. It's a dimer. Okay, so in most cases in the vapor phase, it's an equilibrium between the monomer and the dimer. Okay, so the monomer is a strong Lewis acid because of the electron deficiency of the aluminum center. So the dimer upon formation, right, is able to give aluminum the noble gas configuration. Okay, for the background story, aluminum chloride, is it really an covalent, simple covalent compound? Okay, so over here we have the, I mean, if you do a little bit more research, you'll realize that in the solid phase, aluminum chloride exists as an ionic lattice, okay, with a very large degree of covalent character. Yeah, the covalent character is due to the high charge density of Al3+. Okay, yeah, so if you heat the solid to slightly above 180 degrees Celsius, when Al3 plus and Cl minus, I mean when the solid actually expands, aluminum chloride loses its ionic character, and in the process it will produce the dimer, which is the gaseous molecules. And dimer being a simple discrete molecule, weak dispersion forces between the molecules, so it will vaporize, and therefore it will escape, so-called escape from the surface of the solid AlCl3. Okay, so AlCl3 is very interesting because it's really borderline in terms of bonding. Solid phase ionic, vapor phase simple covalent. Okay, so that is something which you might want to be aware of. Moving on, we have silicon tetrachloride, which exists as a colorless fuming liquid at room temperature. Okay, so again, why is it fuming? Because under ordinary condition, our atmosphere contains quite a bit of water vapor, so it will hydrolyze on the surface of silicon tetrachloride. So in the process, you will get to see white fumes of HCl. Okay, for PCl5 is a off-white solid. Sometimes it appears a bit pale yellow. So it's considered to have a simple covalent structure. This can be largely treated given the context for A levels. Okay, but do take note that at room temperature, the solid phase PCl5 self-ionizes. Okay, so to give us PCl4 plus and PCl6 minus. Yeah, so the solid phase PCl5 has some form of ionic interaction. But once I heat it up to about 160 degrees Celsius, the ionic interaction is gone, because what we are going to have is a simple PCl5 molecules with relatively weak intermolecular dispersion forces. Okay, yeah, so because the forces are easy to overcome, PCl5 sublimes after 160, I mean at a temperature slightly above 160 degrees Celsius. Okay, yeah. For the planning icons, it's quite a generic one, but we are basically discussing inorganic synthesis. How do we prepare simple inorganic compounds such as aluminium chloride? Yep, because sometimes you may be required to plan experiments to prepare and purify inorganic compounds. The techniques in organic chem can also be utilized. So for example, filtration, extraction, distillation, recrease, melting point determination. In fact, if you go to university to perform, to study chemistry, a lot of the experiments in organic and inorganic chemistry will have very high similarities. Okay, so for aluminum chloride as an example, how are we going to prepare it? Okay, so we're going to subject aluminium to dry chlorine in a combustion tube. Okay, and of course in the process I need the anhydrous calcium chloride to also ensure that the environment is moisture free. Okay, and eventually the aluminum chloride form will be sublimed over at this particular region. Okay, yeah, so that so it's actually important for you to ensure that the chlorine introduced is free of water, which means it should be dry. The reason is we don't want our aluminum chloride to hydrolyze in the presence of moisture. Okay, but do take note that anhydrous calcium chloride is very hygroscopic, so just ensure that it's placed you place some in the gut so as to allow absorption of any moisture from the air, particularly when the setup cools. How are gases like chlorine dried? Okay, so it's possible to dry it by passing it through concentrated sulfuric acid. As all of us know, concentrated sulfuric acid is a very good drying agent, so it's able to absorb any moisture. Okay, so earlier on I've done a video showing how a few drops of concentrated sulfuric acid will cause a piece of serviette to combust instantaneously. The reason why that happens is the removal of water from the serviette, right, will result in rapid drying up of the piece of cellulose, and in the process it will decompose to give you char, or give you soot, okay, or carbon based. So it looks as if it is being burnt, but yeah, I mean, you get what I mean. I mean, it's basically just forcing water out from the system. Okay, yep. Then do take note that this particular thing we are introducing here in the planning icon, right, it is a very simplistic view of the whole process of inorganic synthesis. Of course, things are way more complicated than our setup here, but this is just, you know, being put here as I mean, just to show you one example of how we can synthesize aluminum chloride. Yeah, for other compounds there are different ways to make it. If there's a need to, I guess Cambridge questions, if planning is ever required, they will guide you on how to do it. Okay, so not to worry. Okay, next we are going to go on to section 5.3 on reaction of the chlorides with water. Yep, so on the whole, all the chlorides of period 3 will dissolve in water. Dissolve can mean a physical process, or it can also mean to be a process where some form of hydrolysis takes place. Okay, yep. For sodium chloride, it is very soluble in water, and because sodium plus has very low charge density, so it does not hydrolyze further, and sodium plus simply just exists as the naked cation. Yeah, so no hydrolysis, so Na plus remain, I mean sodium chloride solution remain neutral at pH 7. Okay, so basically we are just looking at the sodium plus and chloride being surrounded by water molecules via ion dipole interaction. Okay, for magnesium chloride, again quite soluble in water, and Mg2 plus is often seen as having 6 water ligands surrounding the magnesium cations. Yep, so these are what we call water ligands. So the 6 water ligands surrounds the magnesium cation, and in the process it gives us this particular octahedral complex. Magnesium 2 plus having a relatively high charge density, not very high but quite high in that sense, so it will hydrolyze very, very slightly to give us a little bit of H3O plus. Yeah, so for a relatively decent concentration of magnesium chloride, okay, let's say 0.5 or even 0.6 moles per dm cube, okay, I would expect some bits and pieces of hydrolysis, so we're going to expect a pH value to be about 6.5. Yep, some sources quote as 6.8. I think all are okay, but what we are expecting is a slightly acidic solution. Okay, so just remember that. For aluminium chloride, okay, the reaction with a limited amount of water will produce a white steam of HCl. Okay, and with a large amount of water, you expect the aluminum chloride to so-called dissolve completely or hydrolyze completely, and in the process, the hexa-aqua aluminum 3 plus complex, right, will hydrolyze to a greater extent as that of as compared to that of hexa-aqua Mg2 plus. Okay, so do remember to use these adjectives to help you in your explanation. Okay, so for the hexa-aqua Mg2 plus, it ionized to a small extent of slight hydrolysis to give you a weakly acidic solution. For the hexa-aqua aluminum 3, because it has a very high charge density of Al3 plus, okay, so it will hydrolyze to a great extent or to a further extent as compared to that of Mg2 plus. Okay, the hydrolysis is largely due to the fact that Al3 plus has a larger charge density as compared to Mg2 plus. So being very Lewis acidic, it's able to polarize the OH bond to a very great extent, weakening it, and therefore allowing the nearby water molecules to grab it, and in the process produces H3O plus. Okay, so for the same concentration of Mg2 plus and Al3 plus aqueous, we will predict that Al3 plus aqueous have a much lower pH as compared to Mg2 plus. So in our case here, we predict a pH of about 3 as compared to about 6-ish for Mg2 plus. Okay, I'm going to show you a video showcasing the hydrolysis of Al3 plus, or rather aluminium chloride. Okay, so let me just open up the video for you.
Halides typically undergo hydrolysis. In many cases, the reaction can be vigorous and exothermic. The aluminium chloride is placed in the bottom of a sample tube. In the watch glass to the right of the sample tube, a few drops of ammonia solution are added. In this test, a few drops of water are added to some solid aluminium chloride. Water is added to the aluminium chloride. The hydrolysis of the aluminium chloride forms hydrogen chloride vapour, which reacts with the ammonia vapour, forming a smoke of solid ammonium chloride.
Okay, yep. So I hope you enjoyed the video. Okay, yep. So remember that with a limited amount of water, you are going to get solid aluminium hydroxide with steam white fumes of HCl. With excess water, you are going to get the Al3 plus being formed because it's able to undergo complete hydrolysis. Yep. You will probably not be able to observe the white fumes of HCl. I think earlier on in the video, the placement of the concentrated ammonia solution is really to capture the white fumes of HCl, and in the process produces ammonium chloride, which sublimes at the side of the walls of the container. Okay, yeah. Then moving on, this particular portion, we have kind of talked about it a little bit when we were discussing QA. Okay, so with a controlled amount of OH minus, I would expect aluminium hydroxide to be formed. You can view it as a stepwise ionization process or stepwise acid-base reaction process, or you can view it as the ionic product exceeding the KSP, which leads to the formation of aluminium hydroxide. Yeah. Then in excess amounts of OH minus, yeah, the production of aluminate is favored. Yeah, so because the production of aluminate is favored, it will lead to the dissolution of aluminium hydroxide, because the position of equilibrium will then shift in an appropriate direction so as to produce more aluminate. Okay, so I'm going to explain a little bit more clearly down here, so that the explanation is consistent with what you have seen under the earlier topic on solubility products. And then over here we have balance equations involving carbonate and Al3 plus, but usually I prefer not to write the equation in this particular format. So again, I will discuss it below here. I think I will discuss it before I move on to SiCl4 and PCl5. Okay, yeah. So as promised, I'm going to discuss the Al3 plus first. So I would prefer to view the formation of aluminium hydroxide as the precipitation due to the fact that the ionic product exceeds the KSP. Okay, so that would be Al3 plus with 3OH minus in the process it gives you aluminium hydroxide in the solid phase. Yep. And then the aluminium hydroxide in the solid phase, right, is able to maintain a small amount of Al3 plus and OH minus by virtue of its KSP. Okay, and in the process I'm going to get this. Alright, and as what I've stressed in the solubility equilibrium lecture, in excess OH minus, this particular equilibrium operates, okay, the production of aluminate, so OH minus equals, and in the process it produces AlOH4 minus. Okay, so there are 3 equilibriums in total, or rather 2 equilibriums in total and 1 equation, 1, 2 and 3. So under normal circumstances with a limited amount of OH minus, this will lead to the production of aluminum hydroxide. Okay, and then the aluminum hydroxide being formed will maintain a small amount of Al3 plus and OH minus by virtue of its KSP. In the large amounts of OH minus being added, right, equilibrium 3 will operate, and because equilibrium 3 operates, it kind of disturbs the equilibrium of 2. Yeah, so the Al3 plus will be consumed by equilibrium 3, which leads to the production of aluminates, and this will in turn cause the position of equilibrium of 2 to shift to the right, and therefore what you observe is that aluminum hydroxide, the white PPT, dissolve to give you a colorless complex, which is aluminate. Yeah, and with a small amount of H plus being added, you are disturbing equilibrium 3. Okay, so because you are disturbing equilibrium 3, it leads to the formation of some Al3 plus. Yeah, and the production of some Al3 plus and the presence of OH minus will result in the equilibrium of 2 to shift to the left, and as well as ionic product exceeds KSP, so 1 will lead to the formation of aluminum hydroxide as well. Yeah, and because I do not have enough OH minus to form the aluminate complex, so you are being in a situation where there are some aluminate complex and at the same time there will be some aluminum 3 hydroxide. Yeah, so it's quite a messy situation. Okay, yeah, so I hope you can understand this particular reaction well. Okay, I'm going to use a similar explanation to talk about carbonate. Yeah, but for carbonate, I'm going to discuss the subsequent hydrolysis of hexa aqua aluminum 3. Okay, so I'm going to just explain it over here. Yeah, so as all of us know, aluminum 3 plus in the aqueous phase exists as hexa aqua aluminum 3 complex, okay, which will ionize partially due to the high charge density of aluminum center. Okay, and in the process it gives us this particular new complex. Okay, 2 plus equals plus H plus. Okay, right, this is equilibrium 1. Okay, and what's going to happen is that when I introduce carbonate into the system, carbonate being a weak base, it will immediately source for any available H plus, and in the process it will lead to the formation of CO2 and H2O. So this is the effervescence which you observe. This particular effervescence, the production of this CO2, right, will drive the position of equilibrium of 1 to the right. Okay, and when the position of equilibrium of 1 shift to the right, it will continue to lead to more of the complex ionizing. Okay, so from a 2 plus complex, it will further ionize to give us a mono charge complex, but in this case another water molecule will deprotonate to give us another OH, and then this is a mono charge complex and H plus. Okay, and when we add more and more carbonate, equilibrium 3 will shift to the right, and in the end another equilibrium will operate. Okay, so this equilibrium, when it operates, another water molecules will then be deprotonated, and in the process it leads to the neutral aluminium 3 hydroxide, which we are all familiar with, which is neutral, so it is a solid phase because it cannot form favorable ion dipole interaction with water, so usually it will not dissolve. Okay, you notice that for all this, for the overall equation being showcased over here, right, it is simply a summation of equilibrium 1, 2, 3 and 4. Yeah, so if we add everything up, okay, so this is what we'll get, so we add this, we cancel, and cancel. Yeah, and then we just multiply by 3/2 on both sides, right? Yeah, or rather multiply by 2, so that the appropriate number of moles of carbonate is being used lah. Okay, yeah, so this will eventually lead to the production of the white PBT as well as the effervescence of CO2. Yeah, so you can work out on your own to see whether you can get the overall balance equation. Okay, yeah, so I hope you find this discussion fruitful, because it is very important for you to recognize how the reaction works. Yep. The remaining chloride will undergo complete hydrolysis, and eventually you get a strongly acidic solution due to the formation of HCl. Okay, so for silicon tetrachloride, you will get dehydrated silicon dioxide. PCl5, it will undergo complete hydrolysis to give us phosphoric 5 acid. Okay, so there's a simple way to understand how PCl5 hydrolyzes, and for that matter SiCl4 as well, but I will not attempt to explain for SiCl4. I will leave it to you to think about it on your own, so that again, as I said, there isn't really a need for you to memorize a lot of the equation, because you can easily derive them from logic. Okay, so PCl5, as we know, it has a trigonal bipyramidal geometry. I'm not going to show you the hash and the dash arrows. Okay, I mean the stereochemical projection, because it's not necessary. Okay, so you can imagine that the phosphorus center being highly electron deficient. Okay, so it is susceptible to nucleophilic attack by water. Yeah, so you can just imagine that each of the Cl is being replaced by water molecules. Yeah, but after it's replaced by a water molecules, the oxygen center will take on a +1 formal charge. Okay, so therefore each of the water being attached, right, the H will leave as a H plus, and then you can view it as being combined with with Cl minus to give you the 5HCl. Okay, so that's why there's a 5HCl here. So I hope you can understand. Yeah, so with that, I'm going to just replace all the Cl with OH. So I'm going to get a OH here, and OH here, and OH here, and OH here, and an OH here, plus 5HCl. Yep. And if you could recall, one of the very important idea about chemistry is that an electron deficient center cannot be bonded to too many OHs, because the OH being electron withdrawing, right, will withdraw from the center to make it even more deficient. So they will stabilize the central deficient molecule. So in most circumstances, usually the system will work in such a way that one of the water molecules will be lost to give us H2O, and in the process a new PO double bond will be formed, and that is why over here is +4H2O, because one of the water molecule is being lost as a product. So the earlier 5 water molecules being used for complete hydrolysis, one of it will be cancelled off, so we are left with 4 water molecules reacting with PCl5 to undergo complete hydrolysis. Okay, yeah. Drop-wise addition of water will also react, but in the process, we won't get phosphoric acid. We'll get POCl3 first. Okay, yeah. So I will leave it to you to go and check it out. Of course, over here there's a recall part related to organic chemistry. leading to the formation of the chloride from the nucleophilic substitution of the alcohol groups. Okay, yeah. Do take note that the hydrated silicon dioxide is sometimes written as SiOH4, which is misleading. So in most cases, it should be written as SiO2.2H2O. Okay, I think the way we wrote it here is important. Yeah, so just remember how it's being written. Alright, so with that, we have a summary 5.4 on the properties of chlorides across period 3. So I'll leave it to you to read on your own. Yeah, basically it summarizes what we have discussed thus far. And remember that approximate pH, the initial number of moles of the species remains similar, so that we can compare them easily. I mean, if not, then there is really no point in comparing between apples and oranges. Okay, yeah. So with that, we'll move on to exercise 5.1. Okay, so we have the chloride of element J neither reacts with or dissolve in water. Which of the following could J be? So it cannot react with water or dissolve, okay, in water. Okay, so if you look at all the elements here, aluminium chloride obviously hydrolyzed completely, so cannot be. Carbon tetrachloride, from our understanding, nope, it doesn't dissolve in water because it cannot form favorable hydrogen bonds with water molecules, doesn't react with water as well, so I think the option will be okay. MgCl2 can dissolve, so cannot be MgCl2. SiCl4 will hydrolyze completely in water, so nope, cannot be silicon tetrachloride. Okay, so yeah, the answer would be B. Question number 2. An element of period 3, sodium to sulfur, is heated in chlorine. The product is purified and then add to water. The resulting solution is found to be neutral. Okay, so this is a keyword here. Is found to be neutral. Okay, if you take a look at all the options, right, I think B, C, and D will give us acidic chlorides. Okay, so definitely I'm going to choose A, which is sodium chloride, because sodium chloride is the only neutral chloride in period 3, okay, which we need to be aware of. For questions 3 to 6, there are more than one options which are correct. Okay, yeah. So for question 3, which of the following pairs of compounds contain one that is giant ionic? Okay, so giant ionic, and one that is simple molecular. Okay, so I'm going to highlight the giant ionic first. So this is giant ionic. Okay, then simple molecular, simple molecular, simple molecular, simple molecular. Yeah, so there's only one correct option, which is 1. Okay, question 4. Which of the following sets contains 2 covalent chlorides? Okay, so answer is 2 covalent chlorides and 2 ionic chlorides. Okay, so I'm just going to highlight all the covalent, all the ionic chlorides. So ionic, using the wrong, okay, so I'm going to highlight, okay, ionic, ionic. Okay, so it seems that's quite straightforward because there isn't much choice. ICl is covalent, CCl4 is covalent. Okay, yeah, so with that, only option 1 is correct. Okay, then next, question 5. Why is a solution of aluminum chloride acidic? Okay, so definitely not chloride reacting with water to form hydrochloric acid is nonsense. We all know that chloride will not hydrolyze. Aluminum ion have a high charge to surface area ratio, so yep, some kind of explanation to high charge density, so it will polarize the OH sigma bond to a great extent. So okay, we can take option 2 to be correct. HO bonds are weaker in the hexaalkyl complex than in water. Yes, this is correct as well, so options 2 and 3 will choose. Okay, question 6. Which of the following are correct description of the properties of anhydrous aluminum chloride? Okay, so for anhydrous aluminum chloride, it dissolves in benzene, which is a non-polar solvent, to give a solution which can conduct electricity. This is nonsense because it will remain as a covalent compound in benzene. Okay, so it will not be able to ionize to give us ions. Okay, so 1 is wrong. It fumes in moist air due to the formation of HCl, so this is correct. In the vapor phase, it has a covalent molecular structure. This is correct as well. Okay, either AlCl3 or Al2Cl6. Okay, so I'm going to choose options 2 and 3 for question 6. Okay, so with that, I'm going to move on to section 6. Section 6 gives you a summary of the trends in period 3 elements. Okay, you have seen them before under the topic on chemical bonding. So the first graph shows you the variation in the melting point. You can see that for sodium to magnesium to aluminium, it is a general increasing trend because there's an increase in amounts of electrons being contributed to the C of the localized electron. So there's an increase in metallic bond strength. And you're also getting a more extensive metallic bond going from sodium to magnesium to aluminium. Silicon has a giant covalent structure. Yep, so many extensive amounts and numbers of covalent bonds are required to be overcome in order to melt it. And then from phosphorus to sulfur to chlorine to argon, you notice that there's an increase and then there's a decrease. All these are simple molecular structures where you are overcoming weak dispersion forces between the molecules. Yeah, so the larger, the more polarizable the electron cloud, the stronger the dispersion forces. Yeah, so in terms of the strength of the dispersion forces, from the strongest to the weakest, you expect it to be in the order from sulfur to phosphorus to chlorine and to argon. And that explains why the melting point is in that particular order. For electrical conductivity, I think we explained earlier on as well. Aluminium has the largest number of delocalized electrons being contributed to the C of delocalized electrons. So therefore it will have the greatest electrical conductivity. Silicon is a semiconductor, so you expect its electrical conductivity to be not as high as the rest. And then the non-metals are non-conducting. For the variation in the properties of period 3 oxides, for the oxide, you expect magnesium oxide to have the largest melting point because its ionic bonding is the strongest. For aluminium oxide, you expect the ionic bonding to have some form of covalent character. Yeah, so with that, it's slightly weakened, but that is not to say that if my ionic bonding has covalent character, it contributes to a weak bonding or to a weakness in the bonding. Yeah, it just happened that for the case of aluminium oxide, that is the case. And then for silicon dioxide giant covalent structure, its melting point decreases as well. But that is also not to say that the covalent bond is weaker than ionic bond. Okay, so we are not expected to make that kind of conclusion because that is an inaccurate view of the reality. Okay, but it's largely just for you to take note of the trend in the physical property. Okay, so the physical property here is not meant for you to make conclusions such as whether ionic bonds or covalent bond is stronger. Okay, but of course we can make the conclusion that for simple molecular structure, dispersion forces is definitely weaker than ionic bonding and covalent bonding. Okay, for the reaction of oxides with water, you expect the pH to be in this particular order. I think we have explained earlier on. Sodium oxide hydrolyzed completely to give us a highly alkaline solution, and then MgO, magnesium oxide, ionizes partially and it's not very soluble. Yeah, so therefore it just dissolve a little bit into magnesium hydroxide, and magnesium hydroxide isn't that soluble as well, so the amount of OH minus in the system is kept to a minimum. Okay, so the pH is around 9. For aluminium oxide and silicon dioxide, they are neutral because they are insoluble in water. And then for phosphorus oxide as well as SO3, they hydrolyze completely. So for phosphorus 5 oxide, it gives you phosphoric acid. SO3 gives us sulfuric acid, which is very acidic. Okay, for the chlorides, I think it is in this particular order which is expected. Yeah, for the first two, they exist as giant ionic lattice. AlCl3, as mentioned, in a solid phase as an ionic compound but with significant covalent character, and then in a vapor phase as simple covalence. Okay, so its melting point, in this case the sublimation point, is relatively high. Okay, and for PCl5, it has a larger electron cloud as compared to silicon tetrachloride. So the dispersion forces between PCl5 molecules is stronger than that between SiCl4. Okay, then for the reaction of chloride with water, so then chloride dissolve completely to give us a neutral solution, because sodium plus is not a cation with very high charge density, so it will not ionize appreciably. Mg2 plus ionizes slightly, as what we have seen earlier on, to give you a solution of pH about 6.8. AlCl3 hydrolyzed as well, so the hexa aqua aluminium 3 has, the Al3 plus in hexa aqua aluminium 3 has a greater charge density as compared to Mg2 plus, so the aqua ion will ionize to a greater extent as compared to that in hexa aqua Mg2 plus. Okay, for silicon tetrachloride and PCl5, they hydrolyzes completely in water to give you a strong acid, in this case HCl. Yeah, so the acidity is expected and therefore low pH. Alright, we'll move on to section 7, where we'll talk about group 2. Okay, so the relative strength of group 2 metals as reducing agents can be estimated or seen from the standard electrode potential. Yeah. So as you look at the standard electrode potential, it becomes increasingly more negative. Yeah. So therefore, you would expect the reducing power of the metals to increase down the group. Yeah. So remember that the more negative the standard reduction potential is, the stronger they are, or the stronger the metal is as a reducing agent. Okay, so I repeat, the more negative the standard reduction potential is, or the standard electrode potential is, the stronger the metal will behave as a reducing agent. Okay, regarding thermal stability, this is a very important learning objective. Okay, it is related to nitrates as well. In general, group 2 carbonates are unstable towards heat. One of the main reasons is because carbonate is a relatively large polyatomic anion. So in the presence of a metal cation with relatively high polarizing power, the internal covalent bond will be weakened to a relatively large extent. So that means that the forward reaction where the carbonate will decompose to drive out a small molecule, the probability of that reaction will increase. Yeah, so therefore this particular thermal decomposition, where the carbonate decompose to give us the oxide and the CO2, actually increases. Yeah, the corresponding oxide is actually a lot more stable as compared to the carbonate. One of the key reasons is that the ionic bonding is way stronger, and at the same time the forward reaction is entropy driven. Yeah, why is it entropy driven? Because I am producing a small molecule, in this case CO2. Okay, so you notice that as I go down group 2, the thermal decomposition temperature actually increases. So we conclude that group 2 carbonates become increasingly more thermally stable as I go down the group. This can be easily understood because the charge density of the cation decreases as I go down the group. Okay, remember that all the group 2 cations form cations with +2 charge. Yeah, so as I go down the group with the same +2 charge, the cat ionic radius increases, so that means that the charge density decreases down the group. Yeah, so with that, the polarizing power of the cation decreases, and their ability to distort the electron cloud of carbonate decreases. Yeah, so that explains why the thermal decomposition temperature decreases. One of the main misconceptions students might have is the difference between decomposition and melting. Okay, so remember that decomposition is not, okay, the same as melting or boiling. Okay, so remember this. Decomposition simply means that before the compound melted or vaporized, it gets transformed into another compound, or it gets chemically converted into another compound. So remember that decomposition is not a chemical, it's not a physical process. It is a chemical process. Okay, and in addition, right, decomposition is not burning. Remember this, yeah. Also not the same as combustion. Okay, because decomposition does not involve oxygen. This is very important, so do remember that. Yeah, so let me repeat. Decomposition is not the same as melting and boiling, and decomposition is not the same as combustion. Generally, for decomposition, you notice that on the left hand side of the equation, it does not add anything. Yeah, so on its own, due to heat alone, it will decompose into a more stable compound, as well as it will drive out a small molecule. Okay, the explanation is explained in section 7.2.1, which I have indirectly mentioned earlier on. Yeah, so it has got to do with the polarizing power of the cation, which is related to the charge density. Yeah, so as I repeat, as I move down the group, the charge density decreases, so the polarizing power of the cation decreases. Okay, so therefore that actually means that when the charge density of the cation decreases, their ability to distort the carbonate electron cloud decreases, and the internal or the critical CO bond within carbonate get weakened to a smaller extent. And because they get weakened to a smaller extent, as I go down the group, I will need a higher temperature to effect the decomposition. Okay, yep. So the key explanation is given here. Again, there isn't a need for you to memorize. The main idea is to focus on number one, polarizing power of cation decreases down the group, and therefore their ability to distort the carbonate electron clouds decreases. And then number three, the internal critical covalent bonds within the carbonate gets weakened to a smaller extent. Okay, so with that, it make it harder to decompose, so therefore I require a greater temperature or high temperature to effect the decomposition. Okay, and for the polarizability of the anion, it affects as well. So the larger the anion is, which means the more polarizable they are, the lower will be their thermal stability. Yeah, so usually mono anion do not decompose, so decomposition is strictly applicable to large polyatomic anions. Okay, so the minimum in size, I think you need at least 2. So let's say peroxy anion. Okay, yeah. Right, and then for application example, we have nitrates. Okay, do take note that some of the earlier questions you might have seen in A levels, right, might involve nitrates and hydroxide. The reason being, nitrates and hydroxide used to be in the H2 curriculum, but it has since been taken out. Yeah, so if any questions were to be asked, they are largely focused on application example of decomposition. Okay, yeah, so for nitrates, it will decompose to give us the corresponding oxides, NO2 as well as oxygen. Yeah, I think earlier on in one of the practical example which I have performed in the lab, you will get to see the thermal decomposition of nitrates. Okay, I will provide you with the link below. You can take a look at the thermal decomposition of nitrate at your own leisure, or I can actually attach the video in this presentation.
Okay, students, today I'm going to show you the thermal decomposition of a nitrate. So in this case, we have Fa2 from practical 15. Okay, so I'm going to load it with some Fa2 first. You can see that it's actually a white solid. So over here, so I'm just going to load some in. I'm going to put a bit more so that later on can see the observation clearly. Okay. Going to use a test tube holder. Okay, so now I'm going to switch on the flame. Adjust it a little bit. Okay, so please take note of what you're going to observe. Okay, so make sure that at the start you heat it gently. So swirling it, and do take note of the observation. You can see from here. You can see that some of the solids melted, or maybe it dissolved in its own water of crystallization. Okay, so now you can see that most of it already liquefied or dissolved in its own water of crystallization. So do take note of the color. Okay, so you can see that it's colorless. I think now you can start to observe some of the gases evolving. Okay, so maybe I'll put it near, you can take a look. The gas is a little bit choking. Okay, so you have to be a little bit careful when you're doing this particular experiment. Now, a good heating technique is to always swirl your test tube, because the liquid content is very little. So the development of the pressure will cause the liquid to pump up. So, okay, so over here you see that there's a lot of gases being evolved, and you can see that slowly but surely the solutions begin to dry up. So the decomposition is almost complete. You're driving out combination of water vapor, NO2, NO is a combination. Okay, so you can see it quite clearly over here. Maybe the view is not so clear, but yeah. Okay, do take note of the observation. Okay. Okay, I'm going to increase the flame, the intensity of the flame. Okay, now you observe that it turns into a white PPT with some brown residues. Okay, so right now I'm going to test for NO2. Okay, I'm going to use a blue litmus. We're going to moisten it with a little bit of water for you to observe. Okay. Please observe carefully. Okay, you can observe that the moist blue litmus turns red. You can see that, you can observe that the brown fumes actually evolve out. Okay, if you study it carefully, you should be observing some oxygen given off. So we're going to test the oxygen given off with glowing splints. So we'll see whether it can be observed. Okay, I'm not sure whether the video is clear, but okay, let's observe it. I think it glows a bit more. Okay, let's try again. I think it glows briefly. Maybe we'll try it once more. Okay, very brief. Okay, so that's it. So this is the final appearance. Okay, so you can still see the dense NO2 lingering around the stem of the test tubes. Okay, so that's the end of this demonstration.
And next, we are going to look at hydroxide. So for hydroxide, it will decompose to give us the oxide as well as water vapor, in this case steam. Okay, yeah, so the idea will be the same. You can just look at the cartoon over here, okay, in terms of the polarization and what happened during slight polarization and what happened during further polarization. You notice that for further polarization, the critical or the internal covalent bonds within the anion gets heavily distorted, and then eventually they will form a more stable small molecule. In this case, for our case here, CO2, and then even for hydrogen carbonate, CO2 as well, and then if not H2O and or NO2. Yeah, usually these are the more stable small molecules being formed. Do take note that the process is both enthalpy and entropy driven. Okay, but of course, decomposition itself is a endothermic process because heat is required. Yeah, so by and large, maybe let me just take back the point about enthalpy driven. Okay, well, it really depends as well, but largely decomposition, you can view it as entropy driven because in the whole process, a small molecules is being kicked out and driven off, and they are usually being driven off as gaseous molecules. Okay, yep. And I'm going to move on to exercise 7.1. Which of the following is the correct trend for group 2 elements from magnesium to barium? Okay, so we'll look at all the options. The reducing power decreases. This is incorrect. The reducing power should increase. Yeah. So one of the ways we can look at is either by looking at the standard reduction potential, because from magnesium 2 to barium 2, it becomes increasingly more negative. Another way to look at it would be the valence electrons of barium is further away from the nucleus as compared to that in magnesium. Okay, the elements become more electronegative. This is incorrect as well. Electronegativity value, as we learn in chemical bonding, decreases down the groups. Okay, the calcium cation has the largest charge density. This is wrong as well. Mg2 plus has the largest charge density because magnesium 2 plus has the smallest cationic size. Okay, thermal decomposition temperature of the carbonate increases. This is correct, and we have already verified that in the above discussion. Okay, question 2. Which of the following statements concerning group 2 elements, magnesium, calcium, and barium are correct? Okay, their reactivity increases with increasing atomic mass. This is correct because as we mentioned earlier on, the valence electrons is further and further away from the nucleus, so they are more easily being lost. Okay, so reactivity increases with increasing atomic mass. The only oxidation state exhibited in their stable compound is +2. Okay, this is correct as well because this is a characteristic of group 2 elements. On strong heating, the carbonates are stable to decomposition. This is nonsense. Okay, they are definitely not stable to decomposition. So I'm going to choose options 1 and 2. Okay, yep. So comparison with thermal stability of group 1 carbonate. This is an application example. Group 1 carbonates are usually resistant to decomposition with the exception of lithium carbonate. The reason is because the charge density of lithium carbonate is the highest amongst all the group 1 carbonates, and it's actually quite close to that of Mg2+, although Mg2+ will obviously have a larger charge density. Yeah, so because of that, lithium carbonate, when you subject it to a high enough heat, it will decompose to give you lithium 1 oxides and carbon dioxide as given in the equation shown. Okay, the rest of the group 1 metal cations have low charge density, so I will not expect them to decompose upon heating. I mean in most cases, perhaps before decomposition occurs, they will have melted. Yeah, so usually if we have a cation with an anion that is relatively huge, it's basically a battle between whether the compound decomposes first or it melts first. Yeah, okay, yeah. So with that, we'll move on to section 8 on group 17. For 8.1, we look at the trend in volatility. Okay, so again, we are looking at the size of the electron clouds, and the number of electrons will be a good proxy. Yep, so the size of the electron clouds increases from fluorine to chlorine to bromine to iodine. So with that, we expect an increase in the strength of the dispersion forces between the molecules. Yeah, so because of that, iodine exists as a solid at room temperature, and bromine a liquid. In fact, bromine is one of the two elements which exist as a liquid. The other elements being mercury, which is quite interesting because mercury is actually a metal and is a metal that exists as a liquid. Yeah, so if you read more about mercury, you realize certain interesting chemistry about mercury. Yeah, it actually behaves more like a noble gas. Yeah, due to something known as the inert pair effects, and you might want to read things like relativistic effects as well, which explain why mercury has a very low melting point. Okay, so we will not be touching on them even in transition metal, so I'll leave the readings to you guys. We need to be aware of their colors. Okay, so chlorine is yellow green, bromine reddish brown, iodine is a black solid. Gaseous phase, it will exist as a purple gas. Their color in aqueous solution as well as hexane can be found in the data booklets. Yeah, so it's actually in the second last page of the data booklets. Yeah, so it's the last table right below the second last page. Yeah, so if you are in doubt, do take a look at them. Yep, so because they exist as simple discrete diatomic molecules, dispersion forces exist between them. Yeah, so as I go down the group, the dispersion forces become stronger, and the heats surrounding us in room temperature condition are not sufficient enough to overcome the stronger dispersion forces between iodine molecules. So that is why iodine exists as a solid instead of a liquid or gas. Okay, yeah. For section 8.2, the relative strength of group 17 elements as oxidizing agents. Yeah, so again, we need to look at the standard electrode potential. So you notice that as I go from fluorine to chlorine to bromine to iodine, the standard electrode potential decreases in value. Fluorine has one of the largest standard reduction potential, 2.87 volts. Yeah, so that will explain why fluorine is one of the strongest oxidizing agent known to mankind. Yeah, it has a huge tendency to be reduced to fluoride, and that also explains why fluoride is resistant to oxidation. So it's very difficult to get fluorine. Yeah, so there are other methods to get fluorine, for example, via electrolysis. Okay, yeah, so so this particular section, 8.3, looks at the redox reaction of group 17 elements. Honestly, you have learned them before in secondary school. Yeah, because in secondary school, remember that we often said something like for halogens, the member higher up will displace the anion of the member lower down. Yeah, the reason being you can verify it using the standard reduction potential by calculating the E cell. Okay, I think an example will help a lot more. So if you take a look at exercise 8.1, what observation will be made for the following? Explain your answer with the aid of chemical equation where appropriate. So we are adding aqueous chlorine to a solution of Ki. Okay, so maybe before that, let us take a look at the data booklets. So off the top of my head, if you go and look at the data booklet, you'll be able to get this particular equation. So chlorine plus 2 electrons, it will be reduced to chlorides. Okay, the reduction potential is 1.36 volts as given above over here. Okay, 1.36 volts. Yep. For iodine, so I'm going to write down for iodine. So for I2 aqueous plus 2 electrons, equilibrate to give us 2I minus. The reduction potential is plus 0.54 volts. Okay, and since we are adding chlorine to iodides, okay, so I expect when I calculate the E cell, so E cell should be E reduction minus E oxidation. Yeah, so chlorine is being reduced, so Cl2 slash Cl minus, okay, minus the iodide being oxidized, so I2 slash I minus, so this is equals to 1.36 minus plus 0.54, so I'm going to get plus 0.82 volts. Yeah, so because I get a positive E cell, so I would conclude that the forward reaction is spontaneous. Okay, so with that, I expect the colorless Ki to turn into a brown solution. Okay, so that will be the observation I will make. And then for the balance equation, it will be Cl2 equals plus 2I minus equals, it's a full arrow because this is the reaction that's taking place. I'm going to get 2 chlorides equivalents and I2 equals. Okay, so the observation will be colorless solution of Ki turns brown. Right, next for parts B, potassium bromide solution is added to hexane. So hexane is a colorless liquid with a density of 0.659 grams per cubic centimeters. So therefore it is less dense than water. Yeah, so I will bubble chlorine into the potassium bromide layer. Okay, so first of all, right, before I do anything, I will expect the test tube to be something like this, and then what I'm going to have here is at the bottom I'm going to have KBr aqueous. Okay, at the top layer we have hexane, which is the organic layer. So because it is less dense than water and they don't mix, because hexane, as what we have learned under chemical bonding, it forms dispersion forces with each other and they do not form favorable hydrogen bonds with water. So hexane and water will have 2 layers. Okay, so if I'm going to bubble chlorine into the potassium bromide layer, so I'm going to expect the same idea as above. Okay, so I'm going to calculate E cell. So for E cell, E reduction, which is chlorine chloride minus E oxidation. So let us check if bromides can be oxidized. Okay, the reduction potential of bromine bromide is given here, which is 1.07 volts. Okay, so I'm going to have bromine bromide, so that will be 1.36 minus 1.07. So I'm going to get plus 0.29 volts. Okay, so this is greater than 0 volts. Okay, so I expect the forward reaction to be spontaneous. Yeah, so therefore I would expect bromides to be oxidized to bromine. So for the balance equation, so chlorine aqueous plus 2 equivalent of bromides. Okay, the bromide will be oxidized to bromine aqueous, and then chlorine will be reduced to chlorides. Okay, so with that, I will expect first of all the solution, the aqueous solution, right? For a while it will turn into, let me see the color over here. So it will first turn into orange. Okay, so you expect the aqueous solution to turn from colorless to orange. Yeah, but because bromine being a non-polar molecules, right, it prefers to dissolve in hexane. Yeah, so because of that, I expect there will be an equilibrium between bromine aqueous and bromine dissolving in hexane. Yeah, so the first instance you're going to observe the aqueous solution turning orange, but after a while you will observe that the orange solution lightens, and then the hexane layer will turn into orange red. Yeah, because the color of bromine in hexane is orange red. Okay, yeah, so let me repeat the observation. So first of all, you will observe the aqueous layer colorless turns orange. Okay, and then after that, the color of the orange solution will lighten, and then slowly but surely the colorless hexane layer will turn into a orange red solution. Right, okay, so with that, we move on to the next section, 8.3.2. okay, we have the reactions with aqueous solution containing iron 2. So in the presence of halogen oxidizing solution, an aqueous solution of iron 2 can be oxidized to iron 3. So with exercise 8.2, by calculating the E cell for the reaction between iron 2 and the halogens, show that only chlorine and bromine are able to oxidize iron 2, whereas iodine will not be able to oxidize iron 2. You are given the E cell of iron 3, iron 2. Sorry, not E cell, reduction potential of iron 3, iron 2, okay, to be 0.77 volts. So from here, we're going to calculate the E cell. Okay, so for E cell, that will be E reduction minus E oxidation. So chlorine will be reduced, so 1.36 minus 0.77. Okay, if I take the calculator and punch the values, I'm going to get 0.59 volts, which is greater than 0 volts. So therefore, the reaction is spontaneous. For bromine and iron 2, that will be 1.07, so 1.07 minus 0.77, so I will end up with 0.30 volts, which is greater than 0 volts. So the forward reaction is spontaneous. Yeah, again, if you recall what your tutors in class will have told you, it's good for you to put a plus here, but it's not necessary, because if you don't put a minus, we'll assume that it's a plus. Okay, yeah. For the reaction between iodine and iron 2, yeah, what we're going to get is 0.54, okay, minus 0.77. Okay, so we are going to end up with minus 0.23 volts, which is less than 0 volts. So therefore, the forward reaction from iron 2 with iodine is not spontaneous. And you might also realize that iron 3 is able to oxidize iodide to iodine, and with that, iron 3 will be reduced to iron 2. Okay, I think that is one of the chemistry which you have done in the lab some time ago. Okay, yep, then we're going to move on to the next section on the reaction with thiosulfate. That should be very, very convenient and common, and you have seen that before in JC1. Remember, one of the most important redox titration, which you should be familiar with, is the iodine thiosulfate titration. Okay, that is what we call iodometric titration. So we are all aware that iodine, right, is able to oxidize thiosulfate, the sulfur in thiosulfate, from +2 to +2.5. Yeah. So if I'm going to use a stronger oxidizing agent such as bromine and chlorine, I would expect a higher oxidation states to be reached if they are indeed stronger. Yeah. So so experiment has been performed in by scientists, and indeed bromine and chlorine are able to oxidize thiosulfate from +2 oxidation state, for sulfur, all the way to sulfate, where sulfur takes on its highest possible oxidation state of +6. Yeah, so this actually showcased that chlorine and bromine are stronger oxidizing agents than iodine. Okay, and we can easily understand this again from the reduction potential values, so I don't think we need to go into details. Finally, for 8.4, we have the thermal stability of group 17 hydrides. The reason why we mention this is simply because there is a learning objective talking about it. If not, in most cases, we will not even mention them, because this chemistry is already pretty old. Yep. But you have to be a little bit careful, because over here we are talking about the HX covalent bond strength. Okay, yeah, you are able to get all these values from the data booklets. So do flip over to the diatomics, heterodiatomics molecules to look at the hydrogen-halogen bond strength. Of course, you recognize that HF is the strongest, and we can easily understand that. That is because fluorine is the smallest atoms amongst all, because it's in period 2. So it's being the smallest, it's able to form a good covalent overlap with hydrogen, and at the same time, fluorine is one of the most electronegative element known to mankind. So you expect the covalent bond to have a partial ionic character, or you can call that a polar covalent bond. So the covalent bond strength is strengthened by the ionic character. Yeah, so therefore you expect it to be very strong, and we can see that from the fact that it does not decompose even upon strong heating. Yeah, For HCl, it does not decompose upon strong heating as well, but for HBr, if I heat it strongly, it will decompose to give me hydrogen gas and bromine. Okay, for HI, I will be able to get violet fumes of I2 when I simply put a piece of red hot iron, which means I will heat the iron rods into the Bunsen, in the Bunsen flame, and then I will just insert it into a gas jar containing HI. Then you will notice that HI will simply decompose on the surface of the iron rod due to the heat content on the iron rods. Okay, so this decomposition will occur quite easily. Yeah, and then we have explained to you why that is the case, because down the group atomic radius increases, so I expect the covalent overlap or the valence shell overlap, the valence orbital of I minus of iodine to overlap more poorly with hydrogen as compared to that of fluorine. Okay, so with that, the strength of the covalent bond decreases down group 17, and therefore I need less energy to homolytically break the HX bond. Okay, so therefore thermal stability of hydrogen halide decreases down the group. Okay, then finally, section 9, applying the principle of chemical periodicity. So we have these two unknown LOs, so let us try to see how we can use it to solve problems. Yep, so let us take a look at exercise 9.1. We have element X in period 3 of the periodic table. The following 4 statements were made about the properties of element X or its compounds. Okay, so 3 statements are correct description and 1 is false. Which statement does not fit with the other 3? Okay, so option A, add sodium hydroxide to the solution resulting from the reaction of XL3 with water produces a white PBT, which is soluble in excess sodium hydroxides. Okay, so this kind of implies that X is aluminium. Am I right to say that? Because if you recall what we discussed earlier on, aluminium chloride will hydrolyze completely in water. Hydrolyze in water, and then in the process, it might produce aluminium hydroxide. Okay, and when it will produce aluminium hydroxide when we add sodium hydroxide to it, and then in excess sodium hydroxide, due to the amphotericity of Al3 plus, it will form aluminate, which will dissolve. Okay, because aluminate is a soluble complex. Yep. Let us look at option B. Element X forms a chloride XCl3, which reacts with more chlorine to give XCl5. This is definitely not characteristic of aluminium. In fact, this is characteristic of phosphorus. Okay, yeah, because phosphorus can exist in both +3 and +5 oxidation states. Element X is a solid at room temperature. Is aluminium a solid? Yes, aluminium is a solid, right? Is phosphorus a solid? Yes, phosphorus is also solid. Yep, so this can be either aluminium or phosphorus. Okay, the oxide of X react with water to give an acidic solution. This is definitely characteristic of phosphorus. Okay, because P2O5 or P4O10 hydrolyze in water to give us an acidic solution. So therefore, the only statement that is inconsistent will be statement number A, because statement number A directly pinpoints to the fact that X must be aluminium, but B, C, and D points to the direction that X is likely to be phosphorus. Okay, and you can argue that C is not a specific statement, so it can either be aluminium or phosphorus. Yeah, I'll leave that up to you, but at least B and D tells us that X is phosphorus. So with that, we'll use statement C to our advantage, and statement A is therefore the one that does not fit into the other 3. Yeah, even if you insist that statement A is PCl3, it will not be able to form a white PBT with sodium hydroxide, and then it will not be able to form anything when you add excess sodium hydroxide to it. Yeah, so you will not be able to get that particular observation of white PBT soluble in excess. Okay, next we are going to look at question 2. So for question 2, we have we were told that the use of data booklet is relevant to this question. Okay, so indium indium 49 is used in solar cells and transistors, coats high-speed bearings. From its position in the periodic table, which property would it expected to possess? Okay, so yeah, so let us take a look at the data booklets right now. So indium is over here. Okay, so the question tell us that from its position in the periodic table, which property will expect to possess? Okay, so you notice that indium is in group 13. Okay, and do take note that it is in the same group as aluminium. Okay, so this is quite an important hint for you. Okay, remember this, same group as aluminium. Okay, let's move back. It's in the vapor phase, the chloride has the formula I2Cl6. Does it resemble Al2Cl6? Does it resemble that? Yes. Okay, so we can give that a tick. Its oxide dissolved in aqueous acids. Does that make sense to you? Okay, oxides. That means that indium oxide dissolved in acids. Let us try to recall aluminum oxide. Is it basic in nature? Yes. So okay, so statement 2 seems to make sense. Its ionic salts are highly colored. Okay, this is definitely nonsense. Yeah, because highly colored salts usually characteristic of transition metals. Okay, so this is not characteristic of group 13 elements. So therefore, I will only be picking options 1 and 2. Okay, so next we have the diagonal relationship. This is very, very ancient, and there are usually 3 pairs of elements which we tend to call them having diagonal relationship. So that is lithium and magnesium. I think earlier on we saw that lithium carbonates or lithium salts is the or rather lithium is the only group 1 element where there are carbonates, hydroxides, nitrates can potentially decompose, similar to that of group 2. Yeah, that's because Li plus lithium and magnesium has a diagonal relationship, and that means that their cation have similar charge density, although lithium plus charge density is slightly lower than that of Mg2 plus. Yeah, another pair with diagonal relationship would be beryllium and aluminium, and to a smaller extent boron and silicon. Yeah, this is just concepts which were being introduced to you. Do take note that this is the dotted line, so these are additional information just for your information. They are not meant to be memorized. Okay, yeah. Then moving on, examples of diagonal relationships. So for example, lithium is the only group 1 element that can form nitrite salts. All the group 2 can form nitrite salts. And then BeO is amphoteric because beryllium shares a diagonal relationship with aluminium. Okay, and of course the aqueous solution of Be2 plus and Al3 plus are weakly acidic due to partial hydrolysis. Yeah, and then boron and silicon tends to form covalent compounds rather than cations. Then boron and silicon are both semiconductors. Okay, so these are examples of diagonal relationship which you can I won't say off the top of your head remember, but you can try to reason out by looking at the explanation below. Yeah, so so the explanation below tells us an important fact. If you move across the periods and down the group, the properties tends to be in opposite trends. Yeah, so if you move across the period, atomic radius decreases, but down the group, atomic radius increases. Yeah, and then electronegativity value increases as well, down the group it decreases. Yeah, so if you simultaneously move across the period and down the group by 1 element, the so-called the combined effect kind of partially cancel each other out, but it's not an entire cancellation. Yeah, and do remember that it only works for these 3 pairs. Yeah, please do not extrapolate to other pairs, because generally remember the first member of each group, they are what we call the representative elements, and they tend to have interesting and unique characteristic. Okay, they are quite different from the rest of the elements. Okay, if you are interested in that, please go and pick up an inorganic chemistry textbook and read more. Yeah, we can't cover them in lectures. Okay, yeah. Do take note that diagonal relationship become less noticeable beyond the boron silicon pair. So do not extrapolate. So only those three pairs are the most noticeable ones. Okay, so finally, exercise 9.2, which element is likely to have an electronegativity similar to that of aluminium? So we can easily answer this question by looking at diagonal relationships. Okay, so with that, I'm only looking at beryllium as the answer, because I think earlier on we have already discussed the bulk of the ideas surrounding diagonal relationships. Okay, so with that, we have come to the end of topic 21 on chemical periodicity. Yeah, so your final lecture will be on the transition elements. It's common last topic for the last two batches of students. For your batch, definitely not. So do keep a lookout for it, because it's a very important topic where many questions can be set to combine with other topics such as electrochem, energetics, kinetics, or even chemical bonding. Okay, so do ensure that your understanding of transition metal is very solid before you move on and do your revision and move towards your A levels. Okay, so with that, I thank you for your attention. We'll see you in the next lecture.